In this video, we are going to discuss non-uniform oscillator. Okay, so in the non-uniform oscillator, the mathematical form of the dynamical system which we are going to discuss is the following, which is x dot, which is not x dot, because we are dealing with a flow in the circle, so it's theta dot, right? Theta dot is equal to omega minus a sine theta. Okay, so this is what we are going to discuss. And if you see, this is not an equation which is just cooked up, okay, for the mathematical illustration. It has application in many branches, like we could see a similar equation in electronics, and we see it in biology and in condensed matter physics, and also we will see that equation in mechanics. Okay, so in this lecture what we are going to do is we are going to take this equation and abstractly solve this equation, or trying to see the characteristic of this equation, and then we will be understanding this equation in the branches of science. Okay, so that's what we are going to do. So the first thing is, in this equation we are going to identify the fixed points. Okay, let's try that. So let's plot it. So y is equal to some omega minus a sin x. Okay, now I have to add all the sliders, and let's say initially my omega is more than a, and this is a flow on the line, so I'll be interested only between minus pi to pi or 0 to 2 pi. Okay, so now I am going to consider 0 to 2 pi. Okay, so that's one line, and this is x is equal to 0 line. Okay, now let's just look at this window, and if we see, when omega is larger than a, then there is no fixed point, right? So this is theta dot, and this is not intersecting anywhere at theta dot equal to 0 line, right? So no fixed points. And what will happen to the theta value? So theta dot is positive everywhere, theta dot is positive, so it will keep on increasing, and once it reaches here, once again it will come back and it will keep on increasing. So this is the oscillatory behavior. Okay, since there is no fixed point, it's keep on oscillating. Okay, let's say my omega value is approaching to the a value. Okay, when it's approaching to the a value and exactly become equal to the a value, then we have a fixed point, right? The one fixed point, only one fixed point, and that fixed point is it a stable or unstable? Actually it's neither, it's a half stable, right? And that is happening when theta is equal to pi by 2. Okay, what if my omega is less than a? If I decrease it further, we could observe that there are two fixed points, right? And among these, which is stable, which is unstable? We have to use the same method we have used for flow on the line. Okay, so based on that, the slope is negative, so it's a stable fixed point, where this is a unstable fixed point. Okay, fine. So if I start somewhere from here, I'll be attracted towards this point, and if I start somewhere from here, I will attract it toward this point. If I start somewhere here, I will go all the way, and then once I reach here, I'll come here and then attract it to this point. Okay, so that's how we need to understand this equation. Okay, and if we see the character and the vector field on a circle, it will be in the following manner. Right, so this is the circle, and in this circle, when a is smaller than omega, okay, at that time it will keep on circling. Okay, the only thing is at some places it will go fast, at some other places it will go slow. The reason is, let's say this is the case, right? Yeah, at this region, if you see, it will go fast because theta dot is large, but here theta dot is small, so it will take very long time to cross this region. Okay, so that's what we observe in this figure. So, and also we have observed that the slow will happen when theta is equal to pi by 2, right? So here it's slow and here it's fast. When a is exactly equal to omega, then that will be an half stable. So for that we have to put the picture like this, and for this case there will be two fixed points. One is stable, another one is unstable. If I start somewhere from here, I'll go this way. If I start somewhere from here, I will once again go this way, but in the other direction. Okay, so that's the vector field on the circle. Okay, so now for this case, when omega is greater than a, then we have observed that there will be an oscillatory behavior. So in that case, what is the time period for that oscillation? So that is one thing we'll be interested in, right? Time period. So we'll see how to calculate time period for this one. So time period t, which is equal to integral of dt, which is equal to integral of say 0 to 2 pi dt by d theta into d theta. Okay, so what is this dt by d theta? Which is nothing but inverse of theta dot, right? So what I could write is integral of 0 to 2 pi d theta divided by omega minus a sin theta. Okay, so for this, if we solve, we will get the following, which is 2 pi divided by root omega square minus a square. Okay, so this is our time period, and when, okay, at omega is very near, okay, very near to a, so this whole thing is valid only when omega is greater than a, right? But it's almost near. At that time, what is the time period? At that time, the time period is what we could do is we could rewrite this equation in the following fashion: 2 pi divided by root omega plus a and root omega minus a. Okay, and if they are very close, then I could write omega plus a as 2 omega. Okay, and if we do that, what will I get is the following: pi root 2 divided by root omega into 1 by root omega minus a, and this is valid when omega is very near to a. Okay, so that's the time period. In the next video we will also calculate the time period, but in a different approach. Okay, thank you.